huh? No one. I thought I was late. Yeah, I'm right on time. No one is around. Okay, let me meanwhile check my Moses is here. There. Is this? Good. You did get your shot, right?
My first one, yeah.
Yeah. Did you get the appointment for the second one?
I have not scheduled it.
Yeah. Do you know how to schedule it?
They told me, they gave me a card and they told I think there's a number or something.
So there is this link going around where you can get the second appointment. If I don't send it to you, remind me, I'll send a link to you.
Okay.
I haven't done it for myself yet, but it's floating around among circles. This is word of mouth.
Gotcha. Okay. Yeah.
Did you hear about the vaccine?
My wife and I are signed up tomorrow, so I'm going back tonight. We're driving back down tomorrow.
Oh, you're getting all the way.
It's
Good.
the closest place that is allowing, that actually has.
That's
vaccine.
allowing, yeah, that's the point, yeah. But technically you should be getting it everywhere, right? But it's just that SIU is just very,
They definitely
they have sufficient. Yeah, that's good. That's very good. Yeah. Glad that you're going to drive all the way. That's double driving.
This time I'm going to have my wife drive. I told her.
Good.
She really wants to get it because she wants to go back to the office. And so she said, "Do you want to go back on Friday?" And I said, "I don't, but if we need to do it to get the shot."
That's nice. That's good. I would say, yeah, sort of. So just since morning that email is going on. So I actually wanted to tell that last week to everyone in the class, but I couldn't. Maybe I should use this opportunity to tell it now. Aliyah?
Yes.
Yes, I was wondering, are you aware of the vaccination opportunities that are available in Jackson County?
Excuse me, can you repeat that?
Oh, I was asking, are you aware of the COVID vaccination opportunities that are available in the Jackson County?
Yes.
Okay, so yeah, I just wanted to let you know that people have been using that opportunity and fixing appointments and getting the vaccination. So yeah, it's up to you.
Okay, thank you.
You want to proceed. Jordan, are you aware?
Of what exactly?
Oh, the SIU is, there are COVID vaccination opportunities available in Carbondale, and they have a lot of open appointments, and they are giving it off to people who are not yet eligible. Like technically, our age.
I applied in my area and got denied.
But in Carbondale, they are accepting it and telling.
Oh, okay.
Did I tell that clearly, Moses? Maybe
Yeah. Are they accepting for non-Jackson County residents too?
All my residents.
So if I'm a resident in a different county,
Tomorrow. And they just needed that you're an Illinois resident. That's all they need to know.
Yeah, so that may not work for you then, Jordan. Not being an Illinois resident.
Oh, you're not an Illinois resident, but
no, I live in Missouri.
Check it out. It didn't ask you to be Illinois resident, right?
my wife signed me up, so
Yeah. When I was signing it up, it was even asking the country. So I think as far as you can reach here, you're good. But I don't want to say something that I'm not fully confident about. So make sure you give them a call and
Okay.
Also,
find out.
I have heard, I was talking with Tori, and he tried like 3 different times, and he was denied all 3 times to get the vaccine. And he didn't do anything different than what I did, which is just make an appointment online and just show up. So it sounds, and went to the same center. So it sounds like there's some variability in terms of
Yeah.
what their stance is when you arrive.
Actually, that is correct, because even when I first time heard it, I was thinking that I'm jumping the line. And I actually called Jackson department. This is what I'm hearing. Is this okay? And they told me right away, no, you're not eligible. So I stopped pursuing this altogether. But then 2 days later, everyone around me is getting vaccinated there. And they tried to convince me that, no, you're not jumping the line. I'm not sure yet whether I jumped the line or not. But yeah, that's what is happening. And lots of students and lots of younger people are already vaccinated from what I hear. Many grad students in our department are already vaccinated. I think all the faculties got their vaccination first dose in the department. So that's the news. So from that point on, it's up to you guys to figure out what is going on. Okay. Did that give you sufficient information?
Yeah.
And if you want the link, ask Rob or Moses.
Okay.
Luke and Michael, are you aware of what I was talking about?
I didn't hear much of what you said. My screen went black and I had
see.
to back
First,
up.
Luke, are you aware?
Yeah, I heard, well, I didn't hear the whole thing today, but I heard that some people are getting vaccinated.
Okay. Moses, you want to say? Maybe you will
Yeah.
be better, or
Yeah,
yeah.
what are
I sign up, my wife
I
did it
guess.
all. every-
Okay, so here is what the point is. Okay, and since about 10 days back, I think probably this all started last weekend. There was this email floating around in the university. This was primarily started from the union, faculty union, saying that even though the Jackson County Health Department website says that 65 and younger are not yet eligible, but there were a lot of open appointments available, and the younger people, all the way down to students, have been benefiting by taking the opportunity to take the appointments. And Jackson department have not been saying no to it. And in fact, they have been personally, apparently, encouraging. Okay. So even though officially there is no written document saying that 65 and younger are eligible, lots of them since last 10 days have got vaccinated. And that is apparently there is nothing wrong about it. Okay. So if you go to Jackson County, Illinois Health Department now, you'll find a link for first dose. And you can take an appointment probably even for today. Usually there are sufficient appointments available. Okay. Did I clarify that enough?
Yes, thank you.
Yeah. Again,
Yes,
if
thank
you're interested in the vaccination, that's just it. I thought I should pass on the information. Yeah. Since this is a word of mouth, this is not officially, so it sounds very bad actually. That I would expect that Jackson County should say that first come first basis they should do this, but this is all depending on the word of mouth. That if you have the right contacts, you get it kind of. It all started with apparently doctors telling their friends and their friends telling faculty and faculty telling. It's all word of mouth kind of. It is unfortunate.
Yeah.
But that's what it is. I don't want to blame anyone.
Well, it's possible that they're not
Very aggressive.
not supposed to have as many doses as they do or something. And so, I mean, I don't like, because in other places, people are scrambling to get vaccines,
Yeah, we have.
and we have a surplus. So, I mean, I don't know what's going on there, but
Let's not complain about the good things.
yeah.
But you're getting in that. But yeah, I agree. We lost her. Oh no, Alia is there. Yeah, we lost her for a moment, and then she's back. Yeah. Okay. 1, 2, 3, 4, 5, 6. Yeah. Oh, maybe I should take this opportunity to tell. Yesterday there was a discussion that what if everyone comes in the class? That's nice and all that. We should not forget that if you come and it's all full, we have to go with the limit of the class still. So whoever comes last has to oblige to. I get the freedom to be here because I have to teach, I guess. So other than that, so please oblige and bring your computer also as a safe thing so that you can log in here from another room. Okay, so just warning you, that's possible that 1 month down the line, we might get into a situation where everyone feels comfortable to come to the class. Or maybe not, because Jordan probably will prefer to attend online all through, right? So that's that's a perk, that's a benefit, I guess, which is nice, I suppose. Yeah. So probably we may not reach that stage here. But anyway.
If we ever run into that problem, I will give up my spot and just walk around the corner.
Good, thank you.
And I'll hear the stereo.
Yeah, he shares the wall between his office and here, so he gets double.
Put a stethoscope up to the.
Yeah.
Okay, let's do some. So apparently you have a homework file. Yeah, I think I'm losing track of the numbers. Is this correct?
Yes.
Yes.
March 9th, which is a Tuesday. So there's a homework due today and there's a homework due. I'm a very bad instructor. So many homeworks. Would not have liked myself as an instructor.
Actually, I prefer having a lot of homework because it keeps you on track. The courses that don't give any homework, you have no gauge for what you're, where you're supposed to be.
I thought this last one was, I hate to use the word, but it was kind of fun.
Come again?
I thought that this last one, even.
Oh,
it
it was
kind of
long.
enjoyable. No, it's kind of enjoyable.
Okay.
It was, figuring, especially except for the 1/2 that I lost, figuring out those, how to make that fit, and how to make it work was kind of a thing. And then testing the graphs, checking.
That's good to hear. Yeah.
That's
Because that's what I've been trying to do as a whole course. Like typically this whole course, okay, most of the homework problems that I give is a 5-sentence problem at the most. If you look into Jackson or any other place, this is what it is. What is the magnetic field? And typically that comes out to be very hard, and it's very popular that the subject is very hard and so on. So what I try to do is I take that problem and split it into 5 steps. So I make each step make available so that each of the step is smaller and maybe approachable. That has been my strategy, but often in other subjects, like I tried to do this in introductory level physics a long time back, 10 years back or something. And then students come and ask me, what do you mean by this? This is trivial. Like when you break it into 5 steps, each step sounds trivial. And they're like, why are you asking us to do this? So it didn't work out well with introductory level physics, because when you break their problems, it's why are you asking us to do it? Because especially when you're not seeing the 5th step. In the first step, why? That's too simple. So that didn't work out very well there, but here hopefully, okay. Yeah. So
because there are steps that take 2 pages to do, and there are steps that you can get 2 or 3 parts done on one piece of paper. So it evens out.
Okay, good. Okay. So we talked about magnetic energy. So we said that in some form of like what should say in Lagrangian mechanics or in Hamiltonian mechanics, which is basically a little more generalized version of what we see as the Newtonian equations of motion, when we say time derivative of momentum is force. We say that time derivative of any quantity, let's say m times v in this case, in our particular situation, whenever you have a time derivative of a quantity equaling a negative gradient of something else, q times phi in our case, q times v dotted with a in our scenario, then it is convenient to think of this as a momentum. In fact, not a momentum, you say it is a canonical momentum. And then you would say this is a canonical energy in that sense, right? But it's usually not such this energy. And we said this was the electrostatic energy, magnetostatic energy, and this is the momentum associated. So whenever there is a magnetic field, you suddenly change the definition of the momentum. This should be put in the context of, so for example, the work done by a force, typically you would say is dl dotted with the force F. So if you're, and slightly more important, let's say this is going from R1 to R2, and there is a path along which you. If this was, so that's keeping that in perspective, you should remember how do we define conservative force. Is so conservative force is either you can say the work done along a loop, along a closed path by a certain force is equal to 0, independent of that path itself. And or what you say is that work done by the force about any closed path is equal to 0, then the force is conservative. Or, so this is one implies the other actually. In this case, we can go in series, then you, if the line integral of a quantity is 0, then you can think of it as a surface, like the A dotted with del cross F is 0, right? Like this implies, first step implies a second. That means that if this is 0 for any surface, like remember that this is for any path, right? So this is for any surface, then that implies that del cross F has to be 0. Remember again, because there is this additional statement that this is for any closed path. And the third statement, which is again, one implies the other, but it doesn't have to be in that order, is that if the cross product of a quantity is, if cross product of a vector field is equal to 0, what can you say about the vector field itself? Think about curl of electric field.
Can be written as a gradient.
Good, right? So that means force can be written as a gradient of a potential, if you want, right? In this case, the energy. So these three statements, even though I started from one and went to the other, it doesn't have to be in that order, and all three are related. And in magnetism, this is a little confusing because F is, of course, in, we say this is the Lorentz force, right? And what's your magnetic energy though? So notice if you remember the derivation there was part of it on the right hand side, part of it went into the left hand side for the momentum. So when we say that the work done by a magnetic force is equal to 0, which is a true statement, that doesn't mean that there is, it is very clear that what is the magnetic energy associated with it. So what is the magnetic energy in this sense? What is the force and magnetic energy related? You have to go back. Right? So notice in this way of looking at it, this is coming from the force, right? Force can be written as a del cross F, and that is equal to negative gradient. That is too simplistic. Here it is slightly more, it spreads out in the sense some part of it goes into the energy, some part of it goes into the momentum. Still, this is true. The work done along a closed path is zero, but that's not only at closed path, at each point it is zero. For every tiny path element, it is zero. So all that should be taken with the right attitude in mind. For example, where does this come about? Like these are the discussions that happens, and there's lots of discussions. I would say misleading discussions that goes on and around in the literature, but mostly on the internet. Like literature, I think is better, but internet, as usual, picks on it too much. Like a classic example is work done by the magnetic force is zero. Correct? Is that clear? Yesterday, like the last class, I showed that if the work done by magnetic force is zero, and if you imagine that there is a magnet sticking onto a something and lifts it and puts it somewhere else. Like just imagine it taking it to a certain higher level in gravity. Work has been done. We see that work has been done. So how do you reconcile that fact with the fact that the work done by the magnetic force is equal to zero? So at that time, you have to put all this into perspective, and that goes into the details. That classic example is probably not something that I can show that here. So that's one thing. But let's go back to this. So the magnetic energy, as far as V will be concerned, so let's call it U of M. So this will be the magnetostatic energy would be minus Q V dotted with A. And last time we said that the moment you have this expression, I can write this as an integral. And still, we need to clarify a few things here. So this is minus of integral d cubed r, and this is j of r dotted with a of r. And at this point, we should start clarifying what is going on. There is a current wire typically that is a current density here, and there is probably another current carrying wire which creates this vector potential. Right? Think of two charges. Q1 creates an electric field, and then electric field exerts a force on that. So it is good to clarify that this is J1 and this is J2. So this is 1 and this is 2. This is the current carrying wire labeled as 1, and this is the vector potential created by the second wire. And one might want to release this also, and we will talk about that in a few minutes. So that's the central quantity we want to keep in mind. So we have potential energy to be that, but vector potential itself can be written in terms of J. So our interaction energy, now there is M, since we're talking about only magnetism, let me say this is U12, right? Interaction energy, that's equal to minus mu naught over 4 pi. This also has an integral, so let me say this is d cubed R1, and that is J1 of R1 dotted with J2 of R2 divided by R1 minus R2. sometimes, I think last time I said this, is there a purpose for J1 and J2 here? Sometimes it is convenient to think of this as, I made a mistake.
You're missing an integral here.
Yes, I made a mistake. Thank you. So this is, what's this? Minus mu naught over 4 pi d cube R1, and there's the d cube R2. Right, thank you. So I was saying that is there necessity for this subscript 1 and subscript 2, because I think last class I was saying that, this is R1 is going to take care of the fact that only J1 will contribute and J2 will contribute. Yeah, that is okay. But then we have to be a little more careful. Let us say that if you were to write, so this is just a matter of notation, but still, let's keep this, often this is confusing. So let's say J of R is equal to J1 of R plus J2 of R. So there are two current carrying elements disjoint, and that can be thought of as J1 and J2. And let's say the interaction energy is equal to minus mu naught over 4 pi. Let me actually leave some space there. Leave a little space. I'm going to introduce something there. 4 pi and d cube R1 now. D cube R2. And this time I say J of R, no subscript, J1 dotted with J of R2 divided by R1 minus R2. Okay. And the first question that comes to you, is a question for you, is that, is this the same as the top one? Right? And it's not. So if you notice, J times J is equal to J1 plus J2 times J1 plus J2. Right? That's equal to J1 square, what's that, J1 plus 2 times J1 J2 right, plus J2 right, with the feature that R1 and R2 can be replaced or not. This is an integral, but this is an absolute value, so in fact you can start that. Right? If we are talking about an interaction energy, this is an interaction between one and one itself. And electric wire interacting with itself. Typically that doesn't happen unless you want to write it in this form. But at some advanced level, you do raise the question that can a particle interact with itself. But either way, there is this factor of 2 then. If at all you want to be able to write this, so how you would go about this is that you would say this is, if you want to collect it from J, so you would say this is a factor of half. So often you will see interaction energy written in terms of a single current density J, and there you will see a factor of half showing up. But then if you want the interaction energy between 1 and 2, if there is a factor of half, make sure you divide that by 2, but that is primarily coming because there's an overcounting there in the multiplication, nothing else. There's nothing more fancy than that, but it gets very confusing because first of all, these are divergent quantities. J1 squared will get divergent, but in the standard places that where we look for, we will be looking at interaction energy between two charges or 2 wires, and there is no issue anyway. Okay. With that in mind, I won't say anything more on that.
I have a quick question on your notation. So,
yes.
So your notation, you had J1R plus J2R for J of R. And then in the potential, at the bottom, you have J of R1 times
Yes.
J of R2. And then at the top, you have J of R1, J1 of R1 dotted with J2 of R2.
I'm going to use this because that's very clear.
Okay.
I think that's necessary. But if I were to, so when I'm writing that, I have a separate current density for one wire, separate current density for two. Often it is convenient, or in fact, it is necessary at some theoretical level to be able to associate a single current density for the whole space. If that is a requirement, if that is what you're stuck with, then you have to define something in this form. And then the total energy will be here, which involves an interaction energy between one and one itself. If you want to talk anything meaningful, because they are usually divergent, anything meaningful in the sense, if from what we do typically, then you have to subtract that out. So if you want to talk about interaction energy, you have to subtract out the energy between one and one, assuming that that is even understood properly, and you have to subtract out the energy between 2 and 2, and whatever is left out is interpreted as the interaction energy. This is a real problem. In fact, all the problem that we see in under what is called quantum electrodynamics, you might have heard have you guys heard the word renormalization? Right. So what happens is that at some level, when you want to describe the whole universe, you have to have this current density for the whole, all the charges that is interacting. And then you, in the construction, in the model that we have, we are stuck with charges interacting with each other. So if you want to talk about anything meaningful, you have to subtract that out, but they're all infinities. No wonder, because they're interacting with itself, right? Position of one interacting with the position of the two, R1 and R2 are identical, so that will go to 0. But it is in the model that we have put in, we had to write it like that. But later on, when you are subtracting, you are having infinities in your hand. So you have to subtract them out. And that's what is pretty much, you can say, the one place where infinities begin to crop up. Right? But it is more involved than that. Renormalization involves if you're talking about a particle, is it a single particle or is it a distributed entity? Like the point is, if you're talking about a single electron, is it one point charge or is it all distributed all over space? Right? The moment actually I can put it in the way, right? Is photon a single particle or is it spread out in the whole space? And we know that there are both interpretations possible. The same thing goes for electron. Is it a single particle or is it spread out? And the moment you say it is spread out, if you're ready to accept that, then you don't have this J1. Right? You have an electron that is spread out in space, another electron which is also spread out in space. They will overlap. Wherever they will overlap, you're stuck with R1 and R2 going to infinity. Right? So you're stuck with that, and then how do you subtract them out? And in a very formal, nice way, that is the challenge you face at some level in physics. And this is at electrodynamics level, this has been solved. This is nicely solved. In fact, the author of our textbook is one of them who contributed to that, right? I was just mentioning this to Rob. Schwinger, Feynman, and Kemenagel shared the Nobel Prize for that. But let me stop with that. But I roughly gave a feel for where this shows up. But we will do simpler things. That's not going to do challenging stuff. So, in fact, let me not even talk about the second line, right? I just wanted to say, because often, at least when I was a grad student, I sometimes struggled with that factor of 2. So that's is that a factor of 2 or not? That's a question. Right? So if it is a factor of 2, then you have to think of J in different form. Okay, so with that, let me go back, right? And we will erase that. Okay, so We have J1 and J2. So let's do this for an example, correct? A simple example would be, the simplest example would be, you have two current carrying wires. Let's even keep it of the same length at parallel also, let's say. So they are exactly at the same, let's say, idealized situation. And you have I1, and that is I2. Current I1 and
Well, I have
I2.
one quick
Yes.
question. Sorry
Uh-huh.
to keep
Yeah.
holding back, but so when you think about it in terms of like a Hamiltonian,
Uh-huh.
you know how the Hamiltonian is 2 times the kinetic energy plus the potential energy. So
Uh-huh.
is that the same factor of 2 that comes in? 2
No.
times? No.
No, I don't think so.
Okay.
I don't think so. No. First of all, this is all in I mean, we are not even going to the kinetic energy term. This is in the interaction energy, potential energy itself. But yeah, electrodynamics doesn't respect that very much. It spreads out in both, as you saw in magnetism, right? It penetrates both the momentum and the energy. It spreads out. But simple answer is no, that's not the factor of 2. In fact, I would not even say that it's a good practice to think of Hamiltonian as 2 times kinetic energy plus potential energy. Lagrangian is 2 times kinetic energy plus potential. Is that what you said, right?
No, the Hamiltonian is 2 times the kinetic energy plus potential energy.
No, that cannot be correct. It has to be kinetic energy plus potential energy.
Yeah, that's what I said. Kinetic energy plus potential. So
Oh,
2
but you said
times the kinetic energy plus the potential energy.
Yeah, but that factor of 2 is not there.
Isn't the Hamiltonian 2 times the kinetic energy, which is the energy of the total system minus the Lagrangian?
I see.
Yeah, minus the Lagrangian, yes, but
Yeah.
not minus the potential, or not plus the potential.
I think what you're saying is the following. Yeah, okay. We have a Lagrangian L, and then you would say the Hamiltonian. So L is usually a function of position and velocity, right? And there's a time also, right?
Mm-hmm.
But then Hamiltonian you will define as a velocity, right? Dotted with momentum, correct?
Yes.
Minus L, correct? Which
Yeah.
I think what you're seeing this as is that, this is the, standard. If this was MV, I would say this is P dotted with P over M minus L, correct? So this is nothing but 2 times kinetic energy in certain ways times L. Is that what you're saying?
Yes, that's what I'm saying.
Yeah, but I think don't even do this. Even this is not okay, I think. Like this is it's really necessary that this is a transformation. It's called a legendary transform. It is a transform. You want to keep it in that form because first of all, H has to be, H by construction comes out to be a function of R and P. Okay, and that, notice there is no velocity V, right? One would think that this has V in it, that's a P in it, so there should be a V in it, but this is necessary for that cancellation. And after that cancellation, whatever shows up will be, if you want, often you say this is kinetic energy plus potential energy. That's okay. But again, in R and P, but I would not recommend going this way. There's nothing wrong officially, but I would say it's slightly misleading maybe. That's the best I can say. So yeah, this is okay, but that's not the factor of 2. So I think your question was, is that a factor of 2? No. I would say no. Like we are still in this V itself. We are not even, we do good, okay, but I don't know, Maybe, but my simple answer is no. But often you might be seeing deeper than me right? You might have something. Yeah. Let me not discourage you completely, but my simple answer is no. Yeah. Does it help? Okay.
Yeah.
Okay. Yeah, often these kind of statements I might be misleading you or stopping you from opening up a new lookout altogether. Yeah. So yeah. Okay. With that, let me proceed. Okay. Any other questions? Or proceed. Okay. So two current carrying wires, and I want to keep it fixed length because we already noticed that magnetic field. Oh, maybe I should remind ourselves, right? What is if you have a single current carrying wire, what is the magnetic field? By now, hopefully it is in your immediate thoughts. What's a magnetic field due to just a current carrying wire of infinite length, let's say? Mu dot, yeah, mu dot 4, mu naught over 4 pi, yeah, that's that.
Oh, we're doing, okay, we're not doing the infinite wire.
Let's do infinite wire, infinite.
I over rho.
I over rho 2I over.
2I over.
Okay.
2I over rho, right?
Yeah.
And the direction is phi hat, right? Good, right? What is the vector potential? That's a harder one. Right? So vector potential, cross of what gives you this? And if you recall, this is in the z direction, so this is z hat times mu naught over 4 pi. And we said that, this is not okay because this is infinity. So in the limit length L tends to infinity, this will blow up. And it is true, the length L shows up and it is equal to anyone. 2 times I times log of rho over 2L. Is it rho over 2L or 2L over rho? I think it's rho over 2L. So there is a length dependence L in it, and in the limit L tends to infinity, this diverges logarithmically. So you cannot help it. But since there is a cross, the curl of this, that L goes away. The divergence does not contribute to the magnetic field, right? So if A has this divergence, one can expect that since this was built out of A, and since we are integrating, we are not taking a differentiation, we will have the divergence in the energy also. Right? So one can expect that. And we never talk about this energy in introductory level physics, right? Because that's divergent, right? So we'll always talk about the force, right? Introductory level, we'll say, what is the force between two wires? We never talk about what's the energy between two wires because it's slightly harder to introduce. So let's talk about, so we are going to calculate the energy in that sense. So let's keep this in mind, right? And let's proceed. Okay, so J1 for this would be, let's have J1, R1, right? And let me put R and R prime, how about that? Yeah, let's say R and R prime, or maybe R and R prime, okay. What is this? Oh. Yeah, there's Z hat times I1 times delta of, I had to specify the position of these two charges, right? So let's say this is X minus X1 and Y minus Y1, let's say, right? Okay, so I think that's okay, I guess. And I'm just wondering, should I be using R1 and R2 because it's going to confuse very quickly. Yeah, let me do the following.
You could do delta rho for I1 and delta rho minus A for I2.
Delta rho.
If we say that I1 is at position 0 on the x-axis and then I2 is at position A.
Yeah, that's also actually good enough. Actually. That is sufficient. Yeah, let me not make this too general. Okay, that's I think better. Yeah, let's see. So this is 0. So this is x equal to 0 and y equal to 0. And let's say this is x equal to a and y is still equal to 0, right? I can keep that, right? That's possible. Right? Okay, I think that's a good suggestion. So this is x0. R1, come on, since I've done that there, right? And y1 is 0. Good? I think so. And this is I2 times delta of x2 now is a, and delta of y2 is still 0. Okay, is that visible across the internet? This one,
Yes.
if you want.
Yeah.
Thanks. Okay, so, oops. Yeah. So let's try to get this u12 is equal to mu naught over 4 pi. You have 6 integrals now, right? But they're all elementary integrals because of the delta functions. Del dz1, dz1, dx1, dx, dy1, dx2, dy2, this one, dz2. Right? All minus infinity. Well, all of them are going from minus infinity to plus infinity. You have to write it 5 times. And there's a z dotted with z. There's z hat dotted with z hat, I1 times I2, delta of x1, delta of y1, delta of y2, delta of x2 minus a. I think I listed all of them. And the denominator is x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. I think that's better that we chose that. That's a good suggestion. 4 of the integral collapses immediately. We just have to replace x1 and x2. Z dotted with z is equal to 1. That's equal to minus mu naught over 4 pi. I1 and I2 come out of the integral. And then we have dz1, dz2. And what is left is x2 was 0, x1 was 0, x2 was a, so this is a squared. Y1 and Y2 both are 0, so that doesn't contribute, plus z1 minus z2 squared. Okay, so that's 2. That's relatively simple integral. And
So, really quick, in your original U of 1, 2, is that should that be dx2, dy2, dz2? It looks like dz2, dy2, dz2 on my.
Yeah, there's 2 dz2s. There should one of them should be an x.
it's okay.
Just look 2 integrals to the left of dz2 that you have your right finger on, and you have dz2, dy2, dz2.
Oh, that is actually x2. That I meant to write x2. Yeah.
Oh, okay.
It's nothing to do with the internet because when Moses said dz2, that has to do with my font writing. Yeah, my handwriting. So this is x2. Yeah, I meant to write x1, y1, z1, x2, y2, z. Okay, standard d2, r1. And this is not x. Yeah, this hopefully is better. Z1 and z2. I think you guys have heard about this, right? I have this very difficult problem with writing R1 and gamma. So you guys are more tolerant about this, but this is in introductory level physics. They don't like that. That I write my R1 like this. If I have all the freedom, I write this is my R1. Like, but I try to write this way. That's like, so this is like gamma, right? So yeah, introductory level. So this is something like that. Tolerate me. But you guys are nice. You're at least asking me. Don't get confused. Yeah, please ask. Okay, good. Okay, so this much should be fine, except very standard things we have been doing again and again, right? Trying to do the same systematic so that the idea is clear. Okay, so at this point, whenever we have a square root, we try to substitute this, correct? Let's say, oh, there is something, some catch. I said finite, right? I wanted to keep finite lengths because we are expecting infinities, right? At this stage that comes up. So this should have been, there is a theta of z going from L to minus L, right? Same thing on both sides. Minus L z2 going from L z1 and z2, okay? And that actually forces this integral to minus L to plus L. Sorry, I said that in the beginning, but then I did not implement it. So let's say this is, but they are very symmetrically kept for simplicity. Like any small changes only complicates it. Like it's a good exercise to do what this is inclined, right? All those are nice projects, but very soon this gets very ugly and it's tedious to follow through. That's all. But good, one should be doing all. Okay, so we substitute z1. So let's do z1 integral first, right? So z1 minus z2. You would substitute is equal to a times, let's substitute sine hyperbolic, right? That's what we substituted there when we were doing magnetism, correct? And I think theta is good enough, right? Theta. And then dz1 would be a cosine hyperbolic theta, d theta. I1, I2. And I have dz1 I'm working on. Let's keep dz2 as it is, fixed, minus L to plus L. dz1 I'm working on. So dz1, when z1 is L, or in fact minus L, so I have sine hyperbolic inverse of minus L minus z2 over A. And this is sine hyperbolic inverse of
L minus E.
L minus E, right? And this is, yeah, dz2, no, dz1. dz1 is A cosine hyperbolic theta, d theta. And this is a square plus a square sine hyperbolic square. Remember, in hyperbolic square, cosine hyperbolic square minus sine hyperbolic square is equal to 1. Unlike trigonometry, cosine square theta plus sine square theta is 1. This is minus. So this is 1 plus sine hyperbolic square, then it's cosine hyperbolic square. So the denominator and numerator cancel exactly, including the a's. And dimensions are okay, right?
So that's just A times the
Yeah.
cosine hyperbolic of theta, right? So you just cancel them.
Yeah, so these two cancel out. Yeah. And this is equal to, I'll check my dimensions in a second, but let me write this expression first down. So this is minor V0 over 4 pi I1 I2 times integral going from minus L to plus L dz2. And this is an integral in theta, it's trivial, so it's theta itself, but we have to take the limits. So this is sine hyperbolic inverse of L minus z2. I can write just as z itself, if you allow me. Z2, I'll write it as z. Right. Over, let's write it z2, less confusing for you guys. Okay. Minus of this quantity, but this itself already has a minus sign I can take out, right? So this becomes plus sine hyperbolic inverse of L plus z2 over A. Right? Okay. Oh, yeah, I was going to check the dimension. In a second. Oh, yeah, because you divide out by the. I think so. Okay. Yeah, so notice that this is correct dimensions. Typically, we work with magnetic and is there a way to motivate this better? Magnetic field and yeah. Okay, that's for mine. Yeah, you can check that this is the correct dimensions. I was wondering if it can. Yeah, current and length other than the mu naught over. So that keep that in your mind. Talking about it. Okay. Any comments or questions at this stage? Before I proceed, there's another integral we have to do, right? And I have only 20 minutes. Okay. Okay. So to proceed, let us substitute. Yeah. So basically, we have an integral of this kind. Right? So this is minus L to plus L dz sine hyperbolic inverse of L. Let me do the second one first. L plus z over A, right? That's what it is, right? If I substitute, yeah, first of all, let me show that this is exactly the same as the other. Oh, yeah, let's first do this integral. Yeah. Okay, so let's substitute immediately. L plus z over A is equal to T, right? So dz is equal to A times dt. So this is the same as when it is minus L, this is equal to 0. And when it is plus L, it is 2L over A. dz is A dt. And that's sine hyperbolic inverse of T. Correct? And the substitution you would use for this is think this is substitute sine hyperbolic inverse t. So let me check before. Go ahead.
Should just be able to sub like y or some variable for sine hyperbolic t.
Yes, that is, yeah, that probably, yeah, if you say that is what it is.
Because
also
then
probably
you'll end
is.
up with like
Yeah.
a cosine hyperbolic as your derivative with respect to dt.
Yeah, I think you're correct. Yeah, yeah, I just checked. I wanted to, yeah, so you're suggesting this, correct?
Mm-hmm.
Yeah, so great. So this is equal to, so then you would say this is sine hyperbolic y. I think that's what you were trying to say, correct?
Yes.
Is equal to dt, right? Yeah, I think so. That's equal to a 0 to 2L over a. Oh, now we have to be careful. When t is equal to 2L over a, y is sine hyperbolic. Sine hyperbolic inverse is 0, so this is sine hyperbolic inverse of 2L over a. That's our limits. dt is the sine hyperbolic y, dy, and that is sine hyperbolic inverse, which is just y itself. And why is that equal to do? I think what you do
The
is,
same as the derivative of sine hyperbolic. So dy
yeah,
sine hyperbolic.
that's what I was thinking too. But yeah, no, yeah, you're able to see through all this. It's pretty nice. I'm having difficulty with it. Okay, so this is y dy times y. I think I'm having plans to integrate by parts. I think that's what you're trying to tell. Jordan. So because I want to somehow get rid of this y, so I identify a derivative, right? So this will be derivative with respect to y of sine hyperbolic y. I think that's what you're saying, Jordan?
I think what I was saying is that you would have yeah, but it should be dy of y sine hyperbolic y, right?
Y of y, what?
Oh
This
no,
is correct.
you're right. You're right.
This is
You're right.
correct. Yeah. I mean, this is just an identity, yeah, but you're probably having the right idea ahead that you're going to differentiate by parts. That's remarkable. Good. Okay. Okay. Good. So you integrate by parts then, right? Idea is that you want to kill the y when you integrate by parts. You kill that standard grids that you use and integrate by parts. Good. Okay. So we do total derivative. That's 0 sine hyperbolic inverse of 2L over a y. So this is the total derivative term, which will hit on both y and sine hyperbolic y. That's not completely correct. So let's add a subtract this I 0 to sine hyperbolic inverse of 2L over a. And this time hit only on the y, but that is nicer because then dy integrating on that, differentiating on y is 1. That's sine hyperbolic. Good. That's a tricky use to do integrals. Okay. Good. So this is now doable. A times just evaluate the set the limits, right? This is y is equal to sine hyperbolic inverse of 2L over a times sine hyperbolic inverse of this is nothing but 2L over a in the front. Because if I write it here, so I use parentheses. And minus of 0. So that's 0, minus of 0. Minus a times the integral of this is cosine hyperbolic y. This is the same as cosine hyperbolic y evaluated at 0 and this. But cosine hyperbolic y, I'll write it as 1 plus sine hyperbolic square y square root. So that whenever I take the upper limit, I have an nice feature there. So this is equal to 1 plus 2L over A the whole square root of that, right? And minus of 1. Got captured everything there. Okay, so our energy is currently, really looks very complicated. It is 2L. Oh, yeah, 2L, or maybe start from here, right? A minus A times 1 plus 2L over A the whole square. And finally, we have plus 2L times sine hyperbolic inverse of 2L over A. Let me write this as 2L. Yeah. But this was only one integral, correct? We missed the other integral. But the point is, the other integral was plus C. Instead of plus C, this was a minus C, correct? That was the only difference. Can we follow it through right there? Oh,
You can just flip your in bounds of integration. Just flip it to be.
How are
say
you having
from-
such a clear? Okay. You're ahead of me, Jordan. Okay. So there was this minus Z here, right? This is minus Z. If you do minus Z, so this will be minus Z. And this will be minus dz, right? So this will be plus or minus. Good. Okay, yeah, exactly what you're saying, probably, but let me follow it through, right? So plus dz. So that stays, so this becomes minus, and rest everything goes through, I suppose. Minus will be plus 2L, so this will become 0, but then I'll use the 0 minus sign to change that. So this remains the same, correct?
You should have to flip your bounds of integration from 2L over A to 0, right? I might be wrong about that, but
I'm getting the same integrals, but okay, let's do this quick.
okay.
Okay, let's do this quickly since there's a small confusion there. So if we do minus L to plus L, the other integral was dz sine hyperbolic inverse of L minus Z, right? Over A. So I substitute L minus Z over A equal to T again. So this will be minus dz equal to A dt now. But the limits now, when I put the minus L, this becomes 2L over A. And when I put the plus L, that becomes a 0. So dz is minus A dt. And sine hyperbolic inverse of t, right? Which is equal to, if I use the negative sign to flip the sign. So I think this is still the same. And from that point on, it's everything the same, right? I can keep going. Agreed? So it will be 2 times that integral will be our magnetic energy. Did I convince everybody? Jordan? You're not satisfied? Yeah, okay. So, I'm falling back. Okay, so U12 would be equal then to the minus mu naught over 4 pi. The factor of 2 that I just now talked about, the 2 integrals, that's the 2 integrals. I want to know 2 identical integrals. And the remaining quantity is A minus A times 1 plus 2L over A the whole square and plus 2L sine hyperbolic inverse of 2L over A, right? Okay, good. Remember, we want to, like we did for the magnetic vector potential, this is a divergent quantity in terms of L, but we want to capture the leading terms as much as we can. Or not all the L terms, but the leading terms. Remember, sine hyperbolic x, sine hyperbolic inverse x, we did this in the magnetic case also. This is in terms of log. If we, again, I usually say that one can do this in terms of sine hyperbolic itself, if you're familiar with those expansions, but typically it is easier to remember the log, logarithm instead of the hyperbolic terms. So this is 1 plus x squared. So in terms of this sine hyperbolic inverse of 2L over A, actually keep, there is another 2L there, right? So keep the other one also, so that we want to capture the leading one, right? Capture that, put that also in there. So that's 2L over A times log of 2L over A plus 1 plus 2L over A the whole square. We're looking for the leading terms, so as much as possible, pull out and neglect the rest. For that, first we have to invert it, right? We want something small, so L over A is going to be large, so we want to flip this to begin with. That's 2L over A log of 2L over A times, so this is 1 plus, I pulled out a 2L over A, so that's square being pulled out, so that's 1 plus A over 2L. Did I get this right? This is log of A minus B. Remember, logarithm doesn't distributes non-trivially, right? So one should be careful about that. So 2L over A, so this is log of 2L over A plus, so distribution of the product inside the argument is addition actually. That's 1 plus A over 2L. At this stage, I can start dropping things. If I'm looking for the leading terms, between 1 and a very large quantity, I can drop this. So that gives me a log of 2, but still I have this quantity remaining in here. All right, so this is equal to 2L over A times log of 2L over A plus log of 2. 2L over A log of 2. I cannot get rid of this because these are divergent. This is intrinsically always going to be there. So that's the magnetic energy has that divergence. Oh, I have been going through the board. You guys are nice. Interrupt me. Okay, to change the board. Should I be repeating? Did you guys follow?
We followed.
Yeah. You guys are faster than, smarter than me. Okay. So we have U12 then overall is equal to, go back and minus mu naught over 4 pi 2 times I1 I2 times there also I can start dropping things, but please put this all in there. A minus A. No, I have to do this, correct? Hold on. So I had to pull out, if I want to draw that, I have to be careful. So that's minus A. Pull out a 2L over A. So that then it is 1 plus A over 2L square. Right? So that then I can draw this. And then plus 2L times sine hyperbolic A, we said is plus 2L times log of 2L over A plus 2L times log 2. Just be okay. Hopefully with me. Okay. There is a factor of 2L floating around that surely we can say is because of the overall length of the wire, right? If the length of the wire, there are two infinite wires, then the energy should also be expected to be infinity. So let's define interaction energy per unit length, which will be 2L, right? Let me try to define this as divided by 2L. That's because of the size of the object itself. If you spread out the size itself all the way infinity, then you might not be able to help that much. So this is equal to minus mu naught over 4 pi times 2 times I1, I2. And whatever is left now, I have taken care of the 2L. A's cancel out. And this is, what is this left out? Help here, help.
Well, we're just dividing that
Thanks.
first.
Oh.
Sorry. I mean, if we're just dividing by 2L, then we're just dividing that first term by 2L,
Sure.
and then the 2L's cancel and all the others, right?
Yes, yeah, but I'm a little bothered. I have the next step in my mind, right? So, yeah, sorry, thanks. Plus, this is
I think you're bothered because you can, when you divide by that 2L, you can take an A over 2L out of the entire thing, right? Or no, you can't. Never mind.
yeah, let me proceed. I like this term, but I don't like this term. Yeah. Oh, yeah, I'll kill this because this is small, right? Yeah, okay. No, this is okay. Yeah, good. Sorry. Plus 2L log of 2. Sorry, 2L is good. Log of 2. Yeah, good. Okay, this is fine. But at this stage, you say that, when I'm keeping all these terms, I've already neglected 1 over L terms. So how can I keep this? All this is to leading order in either a constant or logarithm. I haven't, for example, when I expand this, there are terms that I would have killed. This is small. Or take the limit again, right? As much as possible, throw it off. So this is not going to be there. Okay. Is it?
I don't think it would be because if A is a lot smaller than 2L, right, then 2L would force, wait.
Okay, let's keep this term. I feel it is small, but I don't want to drop it now. I don't like dropping that at this point because, okay, let's keep it like this, okay? So let me write this as it is now, if you allow me. So this is equal to minus mu naught over 4 pi, 2 times I1, I2. I know this term is supposed to be there, but still. Okay, so this is the good term, which is the standard term, which will give us the answer. First of all, there are 2 other terms, log of 2 minus log of 1, and I'm keeping this apparently an higher order term. Okay. Plus, of course, order A over 2L. I don't know how many of them I didn't even track them. square, right? I think surely square. That's the only things we have dropped. I think so. Right. That's square. Right? Yeah, I think it's okay. Yeah, this is okay. Yeah, this is perfect. I just have an extra term in this here, which is good. If you want to keep it to this level, then that's what the energy is. Good. Okay.
But if
And
A
I can take extra time, right?
But
Tell the
if A
John?
is a lot smaller than 2L, then that term just disappears, right?
Just disappears, exactly. Yeah. But I was worried that, oh, how can I do that? There will be extra time. But whatever answer I will get, that's the next step. But let me, I want to do a few more things. Yeah. So I have this time, right? You guys allow me to take extra time. So 10 more minutes. Okay. Okay. So that's our energy. And I want to do the step. If I differentiate this energy, I should get force, right? Which is what we study in introductory level physics. You should get that expression for the force, and let's see if we get that. And we'll get some extra term from here, but now I think I have an answer for it. Earlier I was worried. So let's see. So let me pull that here. So this is U12 over 2L, energy per unit length, right? Energy per unit length of the two wires. We have identical wires parallel to each other, so it is okay to talk about per unit length in terms of the both two. Right? That's minus mu naught over 4 pi, 2 times I1, I2, and this is log of 2L over A. These are all constants, minus 1 and plus A over 2L, and I think it is correct to say that this is A over 2L order square, right? So we have the linear term also accurately here, I think. So force between the two wires, let's say magnitude of the force, let us say, force F1 to whichever it is, let's say, force per unit length would be equal to negative gradient, right? But let's not think of it as a gradient, because the moment is gradient, you would say gradient with respect to what, right? There is no position dependence in here. So remember how you define energy or force. Think of it as a generalized concept. This is the description here, right? Two wires, and there is a distance A between them, and the energy is a dependent quantity. If I increase the A or decrease the A, energy decreases. Right? The change in energy with respect to change in A will manifest itself as a force. Energy tries to minimize, so that change should show up as a force. So this is the force due to the change in A. So I will call this derivative with respect to A of U12 over 2L. It's like saying torque is a change in the energy with respect to angle theta and the negative. You can do this for any parameter for that matter. Temperature. Think of a point, and that is what nature does all the time. Nature will always pick that minimization point. So that idea allows us to calculate the force between these two wires, right? And this negative sign is important. I'm going to increase A in that direction, right? So this is 1, that is 2. So I'm going to increase the A in that direction. So if the force comes out to be positive or negative, I'll have a notation there that whether if it is negative, that means this is going to be attractive. Right? So that's some notations involved. Okay, so now take the derivative here. So that's minus mu naught over 4 pi times 2 I1, I2. It's clear that these two do not contribute, right? And there is a minus log of A, so which will be minus 1 over A, right? That's one term you get from the derivative there. Log of A gives you a 1 over A, but it is minus sign because it's in the denominator, I think, or log is minus log A, right? And there is plus 1 over 2L. And which I wanted to neglect, right? Because yeah, plus order, if you want 1 over 2L times order of A over 2L. But in the limit L tends to infinity, this goes to, you don't want to keep this. So this is equal to, if you want, minus and minus gone. So this is mu naught over 4 pi times 2 I1 by 2 over A. This is your classic expression for current carrying wires. Oh, why is it plus now?
I think you, there's an extra negative since U12 is negative and we're taking the minus gradient.
Oh, yeah. There's a minus gradient. Oh, yeah. Good. Thank you. So this is equal to minus of minus, this becomes plus. Thank you. Yeah. So this is minus. Okay. Okay. So this is minus, as I said, if it comes out minus, that means it is going to be attractive, right? It's forces in this direction. And there is a 1 over L term, which I can write minus, and there is plus. But it is small, right, for 2I1, I2 over the length. Right? So this is already force per unit length. Remember, always we talk about the per unit length because these are infinite wires, but this is 0. All these are finite. So plus order 1 over length squared, let's say. So this itself is 0. Right? Here we can neglect that. Okay, that's a time. Okay, I struggled a lot. Sorry. Oh, again, am I not in the screen? Oh, yeah, I am in the screen. Okay, thank you for allowing these times. But I wanted to finish this earlier. I expected this to be short. I had more things to cover. I was thinking that we can do this. Like there is another way of doing this. Actually, I just mentioned that we can also start from the magnetic field instead of the vector potential and get to the same answer, but then you won't get this log of 2 and 1 in that expression. So always the force works out well, but the energy you can be off by some values. And these are deeper questions that are raised usually, that how physical is energy? So like because remember, energy is in many ways more fundamental, you would say, and you cannot really neglect it because, for example, okay, so it seems like there is this term log of 2 minus 1 which doesn't contribute to the force. You can do this exercise in a different way and you don't come across this log of 2 minus 1, and you would say, oh, that's a constant, doesn't matter. But energy is fundamental in the sense it interacts with mass. Right? Energy and mass under gravity attract each other. So the question is that, does these two pieces interact with the mass or not? Is that really there or not? And that's why I want, because we started from interaction piece, right? So I said earlier that you should keep the full piece and then go about it. So that raises a lot of, it leads to ambiguity there. But I'm not saying that that's a big deal. People usually, when done carefully, these things can be handled well. But one has to be careful. Like that's not an unsolved problem. Don't spend too much time on it. Okay, that's all. Any comments?
You could make that a quiz.
Oh yeah, quizzes. We have not had a quiz for some time. Yeah. I like the following quiz better. How about this? A magnet can pick up another magnet to a certain height. But we already said that magnetic force does not do any work. How is that possible? Because the internet is full of these discussions. So you might get a feel for what all I will say. And it can be confusing. It is a little hard to go around it, but it's a good thought-provoking findings. Okay, thanks, Moses. Others might not like you for that.
Is it a similar thing to where I mentioned, I think last semester, I asked you the question, when you lift weights, your muscles feel the weight happening, but whenever you when you let the weight down and you press the weight back up, the work done is 0.
Yeah, but I say that is not, that there's nothing ambiguous there. This is the way I would put it. It's a matter of work done is equal to DL dotted with F, right? With R1, R2, path and all that, right? It's a matter of what we interpret. The work done in standard colloquial language is the work done in the physical sense, right? So here is how I define my work as this is the work done by the force F. That's not me. It's the work done by the force F on the mass M that is moving. There is no ambiguity there. Now, however you want to think of it. Right? There is absolutely no plus minus sign issues that this is the work done by the force F on the mass M. Now, if you want to associate a hand to it, that's different. Yeah, if you say the force is being exerted by your hand, yes, then you are doing the work. But usually it is gravity or the electrostatic force, right? That's not you. So there is no issue with the colloquial language. So this is the work done by the force F. If you are exerting that force F, yes, then you are doing the work. But usually it is hard to imagine which force is your muscle using. So that's that problem, correct? So if you can identify the force that your muscle is using, that's that work. But usually that is very hard, so I'm safe. Right? But the definition here is that work done by the force F. That's clear. It will be the force by you if you know the force. Does that clarify?
I've heard you say that a few times, but I still am confused on how that all comes to play. But I'll do some research into it, I guess.
Yeah. Again, be careful with reading the literature. It's full of, there's a lot of discussion on that. Yeah, don't get carried away. Yeah. But be critical. Yeah, that's all. Be critical. I think there is nothing special to it. Like it's just a if you stick to the definition that it is force F, that's okay. Reasonable?
Yeah, it's just weird that you can do like all other calculations, but
Yeah.
then when it comes to that, it gets a little bit ambiguous.
I feel there is no ambiguity. This is work done by force F. End of story.
You just have to be specific about what force you're talking about.
Yes.
So like in the weightlifting example, the force of gravity does no work on the net path.
Yeah.
But if we were able to identify some more complicated force going on with our muscles, then yeah, maybe we could say there's a non-zero work being done.
Yes.
But we'd have to be more specific about the force that we're talking about.
Does that help? I'm aware of this discussion.
Yeah, I get the wording. None of that doesn't make sense to me. It's just that it's something hard to think about, I suppose. That you need to identify some force that you can't identify in order for it to be ambiguous. I don't know. It's just weird.
Yeah, I think, yeah, tell us, tell me. I'm interested. Yeah, I'm interested in. I feel there is not, but again, I could be missing.
Well, in that case, we would have two different work functions. We'd have the work done by the force of gravity, which is 0, but then we'd have the work done by some other force, which might be non-zero. And that's how we would describe the fact that there actually is work being done. It's just not gravitational work. Right?
Mm-hmm.
So, yeah.
Feel free to criticize me because this is my point. I know that there are chapters written on this, right? So again, I don't want to criticize anyone here, but this is my simple take on it. Yeah. So feel free to criticize.
Hey, Rob,
That's an interesting thought.
did you get my email about the student that wants to do the help desk on Teams tonight?
I got it. Didn't go right before class.
Okay.
All they have to do is go to the webpage, the physics webpage, and it'll link them. Because I'll have it set up. Bob has it set up. I don't do anything other than claim the host position when I go on. So all they have to do is click the link.
Oh, so now there is a physics help that is a link on the website.
Yeah.
Oh, that's very useful. Okay.
He did the schedule on HTML so that he could put links and stuff in.
Okay, good. Yeah. The last semester, I think Luke did his one during that using some link. And then students were asking me, okay, how does this work and all that. So I just said, I'm not involved. Go to the physics office because I didn't want to. Because with undergraduates, they're very particular. You have to give correct instructions. And I didn't want to initiate that. Yeah. Okay.
Or you can give endless instructions and you still don't listen.
Yeah. That's a good point. Good point. Yeah. Yeah. Okay. Good. Okay. But,
Thanks.
yeah. Feel free to criticize me on that. Welcome. But yeah. Hopefully.
No, there's no criticism. It's just
hopefully
it's just
this is
healthy
good.
thought, I think.
Yeah, I know. Yeah. Okay. Good. Enjoy, guys. Yeah.
Thank you.
See you later.
So again,